Welcome again to your channel, Thermal Engineering Concept and Principle. This is Professor Ali Tarrad. I will talk in the present episode about the physics of heat conduction in a plane wall where there is a heat generation per unit volume. Today, I will talk about another type of boundary condition where it is imposed at a plane wall with a heat generation inside that wall, and the other boundary condition such as convection is also to be treated in the present episode. This video will be the last part of the heat conduction in a plane wall series. Thank you for your support, and I hope in this series you have gained some information, useful information, to enrich your knowledge about heat conduction. Let us start with the objectives of the present episode. The objectives of the present video include the one-dimensional heat conduction in a plane wall where there is a heat generation inside that wall. We will use a boundary condition called constant heat flux at the wall. Some case studies will be presented and solved for a temperature distribution inside a wall. And finally, we will arrive to the closure of the present episode. Heat conduction equation in Cartesian coordinate where energy is generated per unit volume of that domain. The element which has been discussed previously in a three-dimension dx by dy by dz and is exposed to heat transfer in the three directions x, y, and z, and this form of equation has been derived in a previous episode in the form partial square t with respect to x square plus partial square t with respect to y square plus partial square t with respect to x square plus q dot divided by k equal to 1 by alpha partial t with respect to tau. And we said that this equation represents the transient form of heat conduction in a plane wall in the three dimension. In this equation, we have alpha as defined before, as which represents the material thermal diffusivity, and the one-dimensional form for a steady state condition has been derived in the form of d squared t by dx square plus q dot divided by k equal to 0. And if we have a look at the figure, q is perpendicular to the surface and has the direction uh, shown in the red arrow. So the general form which we have derived before, and we called it the magic equation, which is used in the plane wall experience heat conduction and heat generation in the steady state conditions, is represented by equation number 4. Of course, this equation will be repeatedly used through this series of videos uh, for applying different boundary conditions.
Let us talk about a boundary condition where a constant heat flux is directed to one side of a wall which experiences a heat generation, and the other face or other side of the wall is exposed to convection, where a fluid is passing with a temperature T ambient and a heat transfer coefficient of H sub A. The solution for this equation, again, we should start from the general form, one-dimensional heat conduction, which is accompanied by a heat generation per unit volume in the wall in one-dimensional form under steady-state conditions. d squared t by dx squared plus q dot divided by k equal to 0. And we have applied two successive integrations. So we have obtained the form of equation 4, which represents the temperature distribution in terms of the position, thermal conductivity, heat generation, and in the form of equation form, that is T of x plus q dot divided by k x squared divided by 2 equal to C1x plus C2. So to solve this equation, we need two boundary conditions to find C1 and C2. The first boundary condition is at x equal to 0, where q equal minus ka dt by dx. And if we apply the flux of heat flux at the surface, then we will have dt by dx equal minus q dot divided by ka equal to minus f divided by k, and that means q divided by a is the heat flux that is directed to the surface. And then if we take this expression and use it in equation number 4, then we will get a form for C1 equal to minus F divided by K. Also, we have a boundary condition at x equal to L that the temperature equal to T sub W. Then T sub W plus Q dot divided by K L squared divided by 2 plus FL divided by K equal to C2. If we substitute the values of C2 and C1 in equation number 4, then equation number 5 represents the temperature distribution inside the wall, which is exposed to a heat flux, that is T of x equal to T sub W plus Q dot divided by 2K times L squared minus X squared plus F divided by K times L minus X. And if we have a look at the boundary condition number 1, which we have used, that is dt by dx equal to minus q divided by Ka, and Q divided by A represents the heat of flux, which is equal to F. And the equation number 5 is the final solution for this equation. And if we have another example for this type of boundary condition, let us consider a surface or a wall that is exposed to constant heat of flux, and the other side is exposed to convection, and we have a heat generation Q dot in units watt per cubic meter with the parameters of the convective side. Then the question is how to find the temperature distribution in the solid wall in terms of the convection parameters. That means in terms of T sub A and H sub A. The solution, again, we have to start from the one-dimensional steady-state heat transfer equation. d squared T by dx squared plus Q dot divided by K equals to 0. And two integrations will produce equation number 4, and we need to apply the boundary conditions when x equal to 0, dt by dx equal to minus f divided by k, and we have also when x equal to L, t of x equal to t sub w. If we apply these boundary conditions, we will get the temperature distribution in terms of TW, and we have this solution from the previous example in terms of equation number 5. Now, how can we substitute the value of T sub W in terms of the convection parameters, and that will lead the final solution of this example. So the heat transfer rate by conduction at the convective wall at x equal to L equal to heat transfer rate by convection, which is at x equal to L as well. If we substitute the values, then we have the conduction part minus Ka dt of x by dx, and where x equal to L equal to h sub A times A Tw minus Ta. If we continue with the solution, then we will get x of L at x equal to L dt by dx equal to minus h sub A divided by k T wall minus T ambient. Equation number 5 gives dt of x by dx equal to minus q dot divided by kx minus f divided by k. Then if x equal to L, then dt by dx is represented by equation number 7. So if we use equation 6 and 7 for dt by dx, where x equal to L, then we will get this form of equation which produces dw, which represents the wall temperature, equal to 1 divided by h a times q dot L plus f plus Ta, which represents the wall temperature. So if we go back to equation number 5 and substitute the value of T sub W, then we will get T of X is a long expression, but again, it's the correct one. T of X is represented by equation number 9, which represents the temperature distribution 1 divided by H of A times Q dot L plus F, close the bracket, plus Q dot divided by 2K times L square minus x square plus F divided by K times L minus X plus TA, which gives the final expression for the solution of this exercise. dt by dx equal to minus q dot x divided by k minus f of k. That means if we take the dt by dx from equation 9, then we will get equation 10. The verification for this equation, dt by dx, which is represented by equation number 10, if x equal to 0, then dt by dx equal to minus f divided by k, which is the same as we have explained during this derivative, which represents the boundary condition number 1. And we have if x equal to L and substitute x by L in equation number 9, then we will get T sub W equal to 1 divided by HA times Q dot L plus F times TA. And then this is the boundary condition number 2, which is also is verified and fulfilled by T of X, which is represented by equation number 9. We have here another example where a wall is exposed to constant heat flux amount to 3 kilowatt per meter square at one face, the x equal to 0, and the other side is exposed to convection, where we have T ambient equal to 30 degrees Celsius, and the convection heat transfer coefficient H sub A equal to 40 watt per meter square Kelvin, and the wall thickness is 2.5 centimeter with a thermal conductivity of 1.5 watt per meter Kelvin, and this wall is experiencing heat generation per unit volume corresponds to 3 times 10 to power 4 watt per cubic meter. The question is how to find the temperature distribution in this solid wall in one dimension. The solution for this one is equation 9, which we have already obtained in the previous example, can describe the temperature distribution, which is represented by T of x in terms of thickness, position, amount of heat flux, thermal conductivity of the wall, and the other parameters. If we substitute these values, then we will get that at x equal to 0, then the temperature corresponds to 180 degrees Celsius. If we use other values for the thickness, 0.5 centimeter, 1.0 centimeter, 1.5, 2.0 centimeter, and then at the surface exposed to convection 2.5 centimeter, and substitute these values in the general form of equation 9, then we will get a temperature distribution. This is starting at x equal to 0 at the side where it is exposed to a constant heat flux is corresponding to 180 Celsius, comes down to 123.75 for T wall exposed to convection, and this can be presented in a form of graphical form in this shape. Then it is a linear variation. It's down from 180 to 123.75 at the wall exposed to convection as shown in this graph. This is another example, which is the same values as those used in the previous example, with a wall exposed to convection, and the other one is exposed to constant heat flux, with all parameters are given. The parameters for convection, T ambient and heat transfer coefficient. The heat generation per unit volume is still the same, the 3 times 10 to power 4 watt per cubic meter, and the heat flux is 3 kilowatt per meter square at the other face, and it is required to compare the result with the case where there is no heat generation. So we need to compare the results between two cases, the first with heat generation and the other without heat generation. And that means still we can use the same form of equations for the case where there is no heat generation as well. Maybe equation 9 is the proper equation or expression to solve this exercise, and that means with replacing or substituting the value of q dot equal to 0, and that will produce t of x equal to f divided by h sub a plus f divided by k times L minus x plus ta, which represents form similar to equation number 9, but we have replaced the heat generation per unit volume equal to 0. And if we apply this equation for the case where x equal to 0, and then we will get a temperature corresponds to 155 degrees Celsius. That is the phase which is exposed to a constant heat flux. If we use the same expression and substitute different values of x for the thickness inside the wall, then we will get a maximum temperature corresponds to 155, 145, and come down to the wall side which faces the convection. The temperature will be 105 Celsius, and that means if we draw the results, it's clear that with the heat generation the maximum was 180, and where is no heat generation the temperature is corresponding to 155, and at the wall that is facing the convective part exposed to ambient, the temperature was 123 something, and then in our final case where there is no heat generation will be 105 Celsius. So almost these curves are parallel with quite different values. I mean, for the heat generation, we will get higher level of temperature zone that what we have for the case where there is no heat generation. Now we have the last part of the episode, which is the closure. We have passed through one-dimensional heat transfer steady state conditions where the wall is experiencing a heat generation per unit volume. Constant heat flux boundary was used in different forms, and case studies were considered for the derivative of the temperature distribution inside these walls, and worked out exercises where we can find such conditions in industrial applications. You may find some useful references in the description box, and this video is the last one for the series, which is related to the one-dimensional heat transfer in a plane wall with different boundary conditions. On the next video, we will talk about cylindrical objects, and thank you for watching, and hopefully we may go through these applications in the near future. And thank you for subscribing and sharing this information with others. And have a nice time, and see you. Bye-bye.